All right, welcome to Physics 208C. This is our capstone class in the engineering physics sequence and covers a variety of subjects that are considered to be modern physics. And by modern physics, I mean basically from 1900 on. And so that may not seem that modern to you, but in the scheme of, say, Isaac Newton, we're looking back, say, 250 years. And so that's older physics. And so modern physics then is around the advent of relativity and the first ideas of quantum mechanics, atomic physics, and then we'll from there move into nuclear physics. And so this class covers a broad range of very non-intuitive topics. And so if you like things that don't make any sense, you're going to love this class because you know, if it looks like it's just outrageous and it shouldn't be that way, then you know, join the club. That's the way it looks to everybody, including me. But that makes it fun because there's a lot of puzzles and there's a lot of things we haven't figured out in the universe. And in modern physics, we get a little bit of a glimpse of that larger reality because when you think about it, the only things that really need to make sense to us are the things that are necessary for our survival. Otherwise, you know, if those things didn't seem reasonable to us, you know, like things follow a well-defined trajectory, and things can only be in one place at the same time, and cause precedes effect. If those kinds of things didn't work or didn't make sense to us, then we wouldn't have survived. And so those are the kinds of things that still make sense to us now, but what we're getting a peek at in modern physics is a larger reality in which the things that we think of as being normal are a small subset of a much bigger reality. And so we get just a little bit of a feeling for what that bigger reality is all about in this class. And so that's why I like it. And it's one of my favorite classes to teach. So you know, you can for sure check out everything on Canvas in terms of the introduction to the course, but I'm just going to get started. And what I want to do here is, first of all, talk about Maxwell's equations. So you may say to yourself, well, I'm an expert in Maxwell's equations. Mr. Clark taught me all about them in Physics 208B. And that may well be true, but what I want to do is use the results of Maxwell's equations to verify Einstein's postulates of special relativity. So that's really where we'll be beginning, is with special relativity in this class. From there we'll move on to atomic physics, quantum mechanics, and finally nuclear physics. So with Maxwell's equations, and this is just a review, we have 4 of them. First one is the closed integral of E dot dA equals the charge enclosed over epsilon naught. So basically this is Gauss's law, and this is electric flux also. So what this is basically telling us is that a source charge will produce an electric field. And it shows us how much of an electric field will be produced by a certain source charge if we do the appropriate integration. The second equation, although maybe not used as often, is the integral of B dot dA is equal to 0. Okay? And so basically what this tells us is that magnetic field lines start and end on themselves. They don't end on source charges. Whereas here, this shows us that electric field lines start and end on source charges. But this tells us that magnetic field lines must be closed loops, because if we integrate around a surface, we're not going to get any source of the magnetic field. Okay, so there's no source charges. Whereas there are source charges for electric fields. Now, some scientists, perhaps a majority of them, would like to expand this and say that there are magnetic monopoles and that they do exist in the universe, and that would give us symmetry to the equations for electricity and magnetism. But they've never been discovered, and for our purposes here, it doesn't really matter whether they exist or not. But since they haven't been discovered yet, we'll keep that term 0. Now, the third equation is our induced electric potential is equal to the integral of E dot dl, okay, and that's equal to minus d magnetic flux, excuse me, dt, where magnetic flux is equal to the integral of B dot dA. Okay, so this is essentially then our magnetic flux in the second equation. And the derivative of our magnetic flux is equal to the integral of B dot dA. So we'll just keep that as an open integral for the moment. And so basically what this tells us then is, let's say, for example, that we're talking about the in this case, a magnetic field through a closed loop. And then let's say that the closed loop were to change its orientation with respect to the magnetic field, then the dot product of B and dA would give us just a component of that. And if it were to rotate continuously, that would create a time derivative of the magnetic flux, and that would generate an electric field. Okay, that's not the kind of situation that we want to look at here. Instead, what we want to look at is a situation where the magnetic field is varying, so it's a function of t across some area A. And let's just for the moment assume that the orientation of the loop stays the same with respect to the magnetic field. Then we can write our magnetic flux then, in this case, as just B times A times the cosine of 0 degrees. And therefore, the derivative of the magnetic flux would be equal to minus dB dt times A. Okay, so this is the special form of the, basically this is Faraday's law that I wanted to look at here, in which we have an induced voltage which causes an induced electric field being caused by a changing magnetic field. Okay? And so there are other possibilities then. There are possibilities in which the loop would rotate with respect to a constant magnetic field. And you looked at all of those kinds of problems, but specifically for the application that I'm looking at in special relativity, we'll just look at time-dependent magnetic fields. So that's B as a function of t. And then we get this form for Faraday's law. And basically then what that tells us, and this is important, and so I'm going to write it down here, is that a changing magnetic field can induce an electric field. So we can get an electric field produced not just by a source charge, as we saw up here with Gauss's law, but we can also get it from a changing magnetic field. A changing magnetic field can produce an electric field too. You don't need source charges to produce an electric field. That's the way that we usually think of as getting an electric field, so source charges. But here we can just change the magnetic field and thereby change the magnetic flux over some area, and we can get an induced electric field through that loop. And then finally, the last equation is the integral of B dot dl equals mu naught I. So this is sometimes called Ampere's law. And then this one here is called Faraday's law. Okay, now this is just a flow of current from, say, charged particles moving through a wire. But it turns out you can get another kind of current too. And this kind of current is called a displacement current. You may have talked about this. I suspect that you did in Physics 208B. Imagine that you've got, say, a capacitor, two capacitor plates, where there is A here, so there's some wire connecting these in, and then there's an electric field that's produced in between the plates, and that electric field for semi-infinite plates would be equal to Q over A epsilon naught, or sigma over epsilon naught. Okay, so at any given moment there's a certain charge Q on these plates. But, and then that Q can relate to the electric flux by this equation here, basically. Okay? And so if we were to differentiate this equation, then we could say that if E is a constant within this region of space times A equals Q enclosed over epsilon naught, and then in this case the source charge would just be the charge on the plates. And so that would be equal to, E would be Q over A epsilon naught. That's basically what we have here from Gauss's law. But if that charge has a derivative, we can say that the derivative of the electric flux with respect to time is equal to d by dt of E times A. That's equal to dq dt over epsilon naught. Or we could call this I displacement over epsilon naught. So here's another kind of current then that we can get from just the change in the electric field. Okay, so if I rewrite this equation, then basically what that gives me is that d electric flux dt is equal to dE dt times A. From this expression, the area of the between the plates remains constant, and so that's equal to I displacement over epsilon naught. Or I displacement is equal to epsilon naught dE dt times A. So this is another kind of current then. And it's caused by, not by flow of electrons between the plates, but it's caused by a changing electric field. So here's E, and as the Q changes from one value to another, the electric field changes and has a time derivative. And so we can think of this as being an equivalent current across the capacitor. Caused by the change in E. Now, you say, well, that's ridiculous because there's no charge flow across an insulating gap of a capacitor. But in terms of the magnetic field that's produced, it's the same as if there were. So the magnetic field that's produced outside the wire here, and the magnetic field that's produced between the plates of the capacitor, if you were to move along here, you wouldn't know the difference. If you were a charged particle, you would see the same magnetic field as you move across the wire and then across between the plates of the capacitor. You would feel that exact same magnetic field. And so this is equivalent then to a current and goes into this expression ID, 4 Ampere's law. And so let's look at the special case where, all right, and this also tells us then that a changing electric field can produce a magnetic field, because Ampere's law tells us that the integral of B dot dl is mu 0 times I, but I is related to dE dt. So that means we can get a source magnetic field produced by a changing electric field. Okay, so look at what these two statements are telling us then. In expression 3, we've got a changing magnetic field induces an electric field. And in expression 4, we've got a changing electric field induces a magnetic field. Okay, so in other words, they can mutually induce each other. And so let's look at the special case here where there are no actual motions of charges. So all we've got is I displacement. So if that's the case, and I displacement is epsilon naught dE dt, then what we've got is the integral of B dot dl equals mu naught epsilon naught dE dt times A. Okay, so this is the special case of Faraday's law that I want to look at. This is the special case of Ampere's law that I want to look at. Okay, and so basically then, if you take these two together and you look at an oscillating charged particle, and let's assume that that oscillating charged particle produces electromagnetic waves. So it can move up and down. It can either be positive or negative. But let's say that it's negative, and it's moving up and down with simple harmonic motion. Then the motion of the charged particle at any given moment will produce a magnetic field, but that magnetic field will be changing with time because the charge at any given moment is changing its velocity. And so therefore the induced magnetic field that's caused by the velocity will also be changing. So that changing magnetic field will induce an electric field. That changing electric field will induce a magnetic field. So we've got something that looks like this, that is mutually inducing itself through space. As a charged particle moves up and down, the changing magnetic field induces an electric field. The changing electric field induces a magnetic field, and then it just keeps going. It just keeps mutually inducing itself all the way from one location to another as a wave phenomenon. And so this is the E direction then, and this would be the B direction out this way. E would be up and B would be out. Okay, and so essentially then the changing magnetic field induces a changing electric field, which induces a changing magnetic field, which induces a changing electric field. So this thing invents itself as it moves along. Okay, and so if we assume solutions to these equations where E is equal to E naught times the sine of kx minus omega t, and B is equal to B naught times the sine of kx minus omega t plus some phase angle phi. Let's take and assume these solutions and plug in to equations 3 and 4 here for Ampere's law and Faraday's law. And we get a solution then. I'll point out that you can check this out in the textbook, see what all of the details are of this solution. But if we assume this and plug into equations 3 and 4, we get a solution. So in other words, the electric and magnetic fields satisfy the traveling harmonic wave equation for an oscillating charged particle, provided that 1, the speed of light squared is equal to 1 over mu naught epsilon naught. So this is the velocity of propagation of the electromagnetic wave. Okay, so it must be the speed of light, and that relates directly to mu naught and epsilon naught. Okay, so this comes straight from making this assumed, taking this assumed form for the solutions for the traveling electric and magnetic fields and plugging them back in to Maxwell's equations. The second constraint on these solutions is that B is equal to E over C. So B naught equals E naught over C, which tells us then that B is weak. And the third condition is that phi is equal to 0, which tells us that E and B are in phase. The speed of light depends on mu naught and epsilon naught, which are our fundamental constants for the strength of the electric and magnetic field. Okay, so where does that get us? Well, basically what it tells us is that you can't change the speed of light without changing the laws of physics. Okay, and so the speed of light has to remain the same unless the strength of the electric or magnetic forces is going to change. And so Einstein then wasn't willing to accept that if you're traveling, say, faster, that the laws of physics would be any different, because who's to say who's moving faster? You know, I could be moving at a certain speed relative to somebody else, but there's no absolute frame of reference for velocity. And so this means that if the speed of light were different for, say, a moving light source relative to a stationary light source, then that means that the strength of the electric and magnetic fields would be different in that reference frame. And that means the laws of physics would change. And so if I were to, say, fly in a rocket ship, 99.9% the speed of light, my atoms would probably fly apart, the rocket ship would explode because the laws of electricity and magnetism wouldn't be working normally anymore. They wouldn't be working the way they're supposed to be working, which is consistently with how they would work in all reference frames. And so to maintain consistency then, our conclusion here is that the speed of light must always stay constant. And so this brings us to Einstein's postulates of special relativity. Now, the first postulate is kind of, I don't know, seems kind of self-evident to me. The laws of physics shouldn't depend on how fast you're going. Okay? And so, in other words, you should get the same measurable observation regardless of which frame of reference you're in. Let's go here to a car that's coming back from the snow and it's moving at 35 miles per hour with respect to the ground. And we have a policeman up here directing traffic, his whistle, and so he's saying, yeah, you can go on through, and so he's going motionless then. But let's say these guys, they came back from the snow, and so they go, let's clobber the policeman with a snowball. And so they throw it at the snowball. They go, it's not going to hurt him too bad. It's only going 5 miles an hour. But that's with respect to the car. Okay? And so with respect to the policeman, then, how fast is that going? I hope you would say 40, right? Because it would be the sum of the velocities. And so the policeman then sees the ball moving at him at 40 miles an hour. Okay, now, in his frame of reference, he sees himself as motionless, the ball moving toward him at 40, and the car moving at him at 35. What the car sees from the car's frame of reference is that the car isn't moving. The policeman is moving toward the car at 35, and the ball is moving away from the car at 5. Okay, so this is from the car's point of view. This is from the Earth's frame of reference, where the Earth is motionless. And you could also do it from the ball's frame of reference. From the ball's frame of reference, the ball wouldn't be moving. The car would be moving away from the ball at 5 miles an hour. And the policeman would be moving toward the ball at 40. So from the ball's frame of reference, it's the ball that's not moving and the other objects that are moving relative to the ball. Okay, so those are your 3 different frames of reference. And basically what Einstein's postulates are telling us is that they're all equivalent because the snowball hits the policeman at the exact same time, regardless of which frame of reference you're in. So it doesn't matter. You know, the laws of physics should be independent of which point of view you choose to be your frame of reference. And so they should all be equivalent. And it makes sense from our normal common sense point of view that the velocity of the ball would be added to the speed of the car. Okay? But that doesn't work that way with light. And so if we go to the second postulate, Einstein's second postulate is that the velocity of light is independent of the light source. Okay? And so that means that no matter how fast the light source is going, the speed of light is going to remain the same. Okay? And so here, if we have a stationary observer that's measuring the speed of light, its distance over time, and then you have a rocket ship that's moving, say, at 0.3 c, and it measures the distance divided by the time, you'd think that the observer that's moving would measure a slower speed of light because it would be almost catching up with the light beam, it would appear. So it would only be moving 0.7 c. That would be common sense. That's the kind of thing that we think of as being normal, the velocities at. But they can't do that with the speed of light. Because if the speed of light were to remain constant, then that means that it can't be different when you're in different frames of reference. But if it were different in different frames of reference, that would imply that the laws of physics are different in different frames of reference. So what we have instead is that all observers will measure the light beam moving at the speed of light. Here's our conclusion then. To keep mu naught and epsilon naught, which control the strengths, or intensities of E and B, to keep mu naught and epsilon naught constant in all reference frames, C cannot vary. Otherwise, we violate the first postulate. So if we really understand the first postulate, we don't even need to state the second postulate, because it's just a natural consequence of keeping the laws of physics the same in all reference frames. And so the question then is, well, if the speed of light remains constant, then does that change anything? And the answer is yes, it changes a whole lot of things.